All right, this is a challenge in a real-world connection problem in our work with parabolas and graphing quadratic functions. So here's the scenario. It's another watermelon problem, and again, don't do this at home, please. This time I launch a watermelon vertically using a slingshot. The slingshot releases the watermelon from a height of 6 feet with an initial velocity of 150 feet per second. So that's a crazy powerful slingshot. Under Earth's gravity, the height of a vertically launched object with an initial velocity and an initial height can be modeled by this quadratic function right here. What's the maximum height reached by my watermelon? So again, let's think carefully about variables and coefficients here. So my independent variable is height right there. My dependent, excuse me, I said that incorrectly. My dependent variable is height, okay? That's what we're trying to sort of calculate for. My independent variable is time, and that shows up in two places as t. So as time goes by, the height of my watermelon changes. And then I have a couple coefficients here. The -16 is just what we are using when we're working with feet and seconds in Earth's gravity. And then the v and the s are numbers that we are given in the scenario. Okay, so let's go ahead and erase all those arrows and see what we need to plug in. So h of t is -16t squared plus the velocity is 150 t, and s stands for the initial height. Looks like the initial height is 6. Okay, we're launching it from a slingshot that ends up being about 6 feet off the ground. All right, what's the maximum height reached by my watermelon? So it looks like what we need to find is the vertex, right? We need to find the vertex of this parabola. To be clear, if we graph time versus height, we're going to start at time 0 with a height of about 6. This parabola is going to go up in the air and then head back down and eventually hit the ground, right? And also to be clear, this parabola I just graphed is not the physical track of the parabola. If we were to graph just the physical track of the parabola, I'm shooting this parabola straight up in the air, so it's going to go straight up and then come straight down, right? And then that's going to be its maximum height. So I'm not graphing the physical track of the watermelon with a parabola. I'm graphing its height versus time with a parabola. Okay. So we want to find this point. Okay. What's the maximum height reached by my watermelon? So this is h comma k, and also to be clear, this h is different from that h, right? The h comma k is those are just the coordinates of the vertex, and the h of t is the height varying with time. Okay, so we have a couple h's to be careful about. Let's just find the vertex, okay? So h, in other words, the x coordinate of my parabola, of the vertex, is -b over 2 times -16. So I think I'll get a decimal. I'm going to go to my calculator for this guy. So I get 4.69. So that means this point right here, the axis of symmetry of my parabola here, is at 4.69 seconds. Okay? It took 4.69 seconds for my watermelon to reach its high point. And that tells you how powerful that slingshot is. Imagine a watermelon being launched upward and it takes almost 5 seconds just to start falling back down. Okay, so let's find its height, and we're just going to plug our h value into our function. So -16 times 4.69 squared plus 150 times 4.69 plus 6. Okay, so we're just going to crank that through our calculator and see what the k value is for the vertex. And I get a k value of 357.56, and this is all in feet. Okay, so let's be clear. Our vertex, which is h and k, is 4.69, 357.56, which means our maximum height is this value right here of about 358 feet. So that's a pretty high launch of a watermelon. Don't try this at home. Okay, good place to stop.